Today we're going to get a little bit more into thermodynamics and free energy and exactly looking at what that means for a reaction and how we can use that information to determine is a reaction spontaneous or not, and more importantly, what direction would a reaction be, spontaneous or not. So Chapter 11 is the only homework that's due this weekend. That's due Sunday, July 26th at midnight. I'll also have my review session Sunday night, 8 to 9 p.m. if anyone has any questions. Right now, we are 1 day behind schedule. We spent a little bit more time on some of the material leading up to the midterm exam, so we're just 1 day behind the schedule of the calendar that I handed out at the start of the semester. So last class we talked about entropy, a way to help quantify changes that are taking place in a reaction with respect to why does a reaction happen in the direction that it does, right? We're looking at there must be some factor that's helping us spread energy around, and that's entropy. And we looked at ways of increasing entropy through increasing the volume of a system or increasing the temperature of a system, increasing how many moles are in that system, or going through a phase change from solid to liquid to gas. Because entropy is the measure of how many microstates we have in that system. So think of entropy as how many frames we have in a movie. If the system was a movie and we took a picture every fraction of a second, every millisecond, right, each of those pictures would be a microstate because all the molecules within that system, they'd be in a different place, they'd be in a different arrangement, a different configuration. So the more pictures we need to describe all the possible arrangements of all the molecules in that system, the more microstates we have and the more entropy we have in that system. So here's a good question, kind of looking at ways we can increase the entropy of a system. So we've got our initial system that consists of a cylinder with a piston containing 10 to the 6 gas molecules. It's at 298 degrees and 1 liter. We're presented with 5 different systems and asked to rank them in the order of decreasing number of microstates. So from most microstates, most entropy, to least entropy, right? Most entropy to least entropy. So we have choice A, our initial system. We have choice B. We go from the initial system and then we increase the volume and we increase temperature. We go from 1 liter to 2 liters and we go from 298 to 395. So we did 2 things to increase the entropy. Choice C, starting from the initial system, a combination reaction occurs at constant volume and temperature. So we don't change volume, we don't change temperature, but a combination reaction. And a combination reaction would be like A plus B goes to C. So the end result of that, if I have 1 mole of A, 1 mole of B, they both react, I'm going to be left with only 1 mole of C. So I'm going to have a decrease in concentration. D, starting from the initial system, the gas reacts completely to produce 10 to the 7 gas molecules at 395 and a volume of 2 liters. So here we've increased the concentration, right? We've increased the number of moles, we've increased the temperature, and I've increased the volume of that sample. And then last but not least, E, we start from the initial system and we increase the temperature to 395 Kelvin. So let's see, to rank these from most microstates to least microstates, right? Choice D, system D, would have the most microstates because we increase concentration, we increase temperature, we increase volume. We did 3 things that all lead to an increase in entropy. So next we would have choice B, because we've increased the volume and increased the temperature. After that, we would have choice E because we've increased the temperature. Finally, we would have choice A, our initial system, and then our last system would be choice C. C would have the fewest number of microstates because we actually decreased the entropy. We went through a reaction that resulted in a decrease in the number of moles, a decrease in the concentration. So we actually did something that decreased the entropy from the initial system. So from highest entropy to least entropy, it should be D, B, E, A, and C. So yesterday we talked about the third law of thermodynamics. We're going to spend a little bit more time looking at that today. And the third law of thermodynamics basically states that at absolute zero, which is 0 Kelvin, there is 0 kinetic energy. Right, remember our definition of temperature is the average kinetic energy of the sample. So if we are at absolute zero, there is 0 kinetic energy in that sample. So that results in no molecular movement So let's see what that says for my microstates. If I have a system at absolute zero, there's no movement. These molecules are in a perfect crystalline solid. They are not able to move at all because their average kinetic energy, the temperature, right, is 0 Kelvin. So if I want to calculate the number of microstates, right, and the entropy of this system, entropy would equal Boltzmann's constant times the natural log of how many microstates do I have? Well, if this system is at absolute zero, nothing in that system is able to move. So how many microstates would you need? You would need enough microstates, right? Enough pictures of this to describe all possible arrangements. If nothing is moving in this system, right, one picture would suffice. One picture would describe all the possible arrangements. So I would have one microstate, and the natural log of 1 is 0. So I take the natural log of 1, that's 0, multiply that by my Boltzmann's constant. Entropy would be 0. So at absolute 0, there is 0 entropy. So for a pure crystalline solid, at absolute 0, the entropy is 0. And what that means is I increase the temperature. If I raise the temperature of that from absolute 0, I would only expect to see an increase in temperature, right? So as temperature increases, entropy will increase. My molecular movements will start to increase, right? Things will start to move around in a couple different directions or back and forth. And as a result, I get more molecular movement, more microstates, more pictures, a greater degree of entropy. So absolute 0 is defined as 0 degrees Kelvin. And at 0 degrees Kelvin, the average kinetic energy is 0. And because there's no kinetic energy, right, the entropy of that system would also be 0. We can also take a look at entropy increases, and sure, as we increase temperature, we're increasing entropy in general. Let's take a look at that over a phase diagram. As we've got going from a solid to a liquid to gas, again, we see entropy increases. As I increase temperature, I see an increase in entropy, but we notice there's something interesting along these transitions between the solid to liquid and liquid to gas phase. I get large jumps in entropy. Those large jumps in entropy are the result of a phase change, right? I'm going from a solid to a liquid, and here I'm going from a liquid to a gas. I'm getting a large change in entropy because as I go from that solid to the liquid, I've got more molecular freedom, more movement, more microstates. And the same thing when I go from the liquid to the gas, I'm increasing the molecular freedom, increasing the number of arrangements, increasing the microstates, and increasing the entropy. So I can increase the entropy by increasing the temperature, by going through a phase change, and also in general, the standard entropies tend to increase, so they get increasing molar mass. So as the molecules get larger and larger and larger, I'm going to have an increase in entropy. And so here's the entropy for these molecules, right? Hydrogen is just 2 grams per mole. Nitrogen is 28 grams per mole. Oxygen is 32 grams per mole. And so as I increase the molecular weight, again, I increase the entropy. All the way down to benzene, which would be the largest molecule on this list, has the largest entropy. We can also compare the entropies of the phases, right, to confirm that water vapor, water in the gas phase, has a much higher entropy than water in the liquid phase, because I've increased the amount of separation, I'm increasing the speed of those molecules, the average kinetic energy of those molecules, increasing the entropy of that system. So here's a question for you. When thinking about that, right, why do larger, more complex molecules have larger entropies? So here we have methane, ethane, and propane. Ethane is just 1 carbon and 4 hydrogens. Ethane has 2 carbons and 6 hydrogens. And propane, we have 3 carbons and we have 8 hydrogens. So why does entropy increase? Got 186 joules per mole Kelvin, 229 to 270 from methane all the way up to propane. Well, larger, more complex molecules have more entropy because, thinking about it, right, we have more bonds that can move. So within this sample of methane, sure, I can stretch these carbon-hydrogen bonds. But here, within ethane, I can rotate around this carbon-carbon bond, kind of like thinking of like a windmill spinning around its top. The same thing can happen here, and while that's happening, these carbon-hydrogen bonds can also stretch in opposite and different directions, and they can wave back and forth as well. Now I've increased one more carbon-carbon bond, so I can rotate here in opposite direction. Right? Just increasing the number of possible conformations this molecule can be found in, because I'm increasing the number of possible conformations and possible movements that molecule can go through, I'm increasing the entropy of that molecule. So larger molecules tend to have more entropy because they have many more bonds and movements, arrangements available. Right, I would need more pictures then to describe all the possible shapes that propane can take, because I have so many more bonds that will be moving in all different directions all at the same time. So in general, as molar mass increases, so does entropy. In our next module, we're going to look at how to calculate the entropy and a change in entropy during the course of the reaction.